Okay, welcome to class meeting 14 of EECE574, the graduate level probability and random processes. There are a few important announcements. First, we will have the first midterm exam on this Thursday evening here in LG 102. And it's an open everything exam except any human interaction, remotely or closely. Got it? And second, no class meeting on this Thursday. Homework 10 was supposed to be assigned, but I found myself very busy, so there will be no homework 10 until exam. So that's happy. Handouts are uploaded, so we will today use a different handout from the previous one. Lecture videos are available as you see here. No special corrections, clarifications this time. We started this new topic, time average. So let's see what it was. So we first started to define the average of a deterministic signal. Sorry, not this one. Yeah, got it. Okay. So average over deterministic signal. That was an integration over deterministic signal on a finite interval of length, in this case, 2 capital T. The important thing is that here, the term average is attached because we not only integrate, but also divide by something. When we talk about arithmetic average of 5 numbers, we divide the sum by 5, right? Here, the integration corresponds to the summation, and this 2t corresponds to the number of added numbers, right? So the name average makes sense. However, the problem is that when we just say this is the average of x of t over this period. And we may wonder what happens if we take the length of interval to infinity by covering all the interval. You must be careful in this definition. For example, sometimes your x of t is defined only a infinite interval, but a semi-infinite interval. So you can choose your time origin, say 0, and integrate up to plus infinity, but no negative time. In that case, probably you want to define time average as limit t tends to infinity, 1 over capital T, integral from 0 to capital T, x of t dt. So this definition can be varied depending on your situation. So be careful. Another one, last time I didn't say, but you can have some strange averaging like this. So here you started from negative t to t, but you may choose, for example, negative t to capital 2t. In that case, your negative t part grows linearly and positive t part grows linearly, but twice faster. But if you take t into infinity, t to infinity, anyway, entire interval of your interest will be covered, right? So sometimes that may work, but be careful. In that case, if this is negative 2t and this negative t and this is 2 capital T, then you must divide by 3t. It's obvious, right? Anyway, so the first, you construct the function. And here you have a kind of infinite number of averages, and you consider the limit of it. So it's similar that your integral is a function of capital T in this case. And you have some new function, f of capital T, and you consider the limit of this function when t tends to infinity. For example, suppose f of capital T turns out to be 1 over capital T. Then what is the time average in that case? By this definition, it's 0, right? Because if t tends to infinity, it converges to 0. So even though individual integral may not be 0, sometimes your average can be 0. So this is a function of t, and this is, if it converges, a constant, right? So you have a function, real function of t, and you consider the limit of it. Now, let's see this special case. So it's a review. If signal is a constant signal, then its average is the constant, right? It's obvious because if you integrate this one, this becomes C. So it's obvious. Now, here goes the definition of energy of a signal. So you are given a deterministic continuous time signal. You can do the same thing for a discrete time signal. And what you do is that you take the modulus square. If it is complex function, we have to say modulus, but we usually say absolute value anyway. So absolute value square of x of t, and you integrate over the entire interval. Actually, this can be interpreted as a limit t tends to infinity, integral from negative t to positive t, right? This integral must be interpreted in that way. So you always have a finite interval and take the length of interval to infinity. So you have a kind of construct a function of interval length and consider the limit. If this limit, right? This is this limit exists or it has a limit, then we call it an energy. And if this is finite, we call this signal a finite energy signal. Interesting thing is that we usually say that the zero signal, we must be careful, but energy is, if a signal is zero, for example, x of t is zero, then the energy is zero. But some signal, which is not always equal to zero, can have energy zero. For example, you have a zero function, but at time zero, its value is one, not direct delta, its value is one. Then if you square and integrate, then you still have zero, right? So be careful. But anyway, so we put the restriction that if energy is positive but finite, then we call the signal an energy signal or a finite energy signal. Got it? Interesting thing is that this definition is translation invariant, which means that if you define y of t as x of t minus some delay, and then x and y have the same energy. Now, similar to the definition of energy, we define the power of a continuous time signal. And this power of continuous time signal is, first, you compute the energy inside an interval and divide by t. Here, the interval has unit time, second or some minutes. So if this is in joules, then this becomes in watts. And then you take the infinity. You take t to infinity. Then this may converge or not. If it converges to a positive finite number, we call x of t a finite power signal or simply a power signal. Using this time average notation operator, we can define the power of signal. Here, x means you compute x of t times x of t conjugate. But anyway, so you can rewrite the power of the signal as the average, time average of what? Instantaneous power. So if this instantaneous power is constant, then the average power is the same as the constant. So this is so-called instantaneous power of a deterministic signal. By the way, as I told you, this can be interpreted as limit t goes to infinity. Without divide by 1 over t, you have negative t to t, x of t squared dt. Got it? So the difference is simply this 1 over the length of the interval. In general, an energy signal, finite energy signal has zero power. And a power signal has infinite energy. That's obvious. And the power is also translation invariant. So if you define y of t as x of t minus some delay, then the power of x and power of y are the same. Now, we define the time autocorrelation function of a deterministic signal. And that is x of t and x of t, t minus tau dt. And you integrate over the interval of length 2t, so you divide by 2t. And you integrate. If, as a function of capital T, if it converges to a finite number, then it is defined as the time autocorrelation function of x of t at tau. So this function is a function of tau now. And similar to the previous one, this time autocorrelation function can also be rewritten using the time average operator A in this textbook. Some other books use totally different notation, so be careful. And as you see, this is the correct or immediate definition, because you have x of t minus tau conjugate. That is averaged, right? So you can rewrite this part as some z of t, then this is simply time average of g of t. But using the translation invariance, actually, you can rewrite this one as that one, or if you want, like this. And sometimes this definition of time autocorrelation function is more useful. Sometimes this is useful, sometimes that is useful. But the commonality is like this. I recommend you to put conjugation on the right factor, the right side factor. You multiply 2, right? So please put conjugation to the right factor. And you subtract the arguments from left to right. So this left minus right becomes tau, which is the parameter of your time autocorrelation function. That is very useful and consistent. So when I memorize this, okay, the right guy has something conjugate. So it's happy. Left guy has tau, so it is also happy, right? And here, left guy does have nothing, but right guy has conjugate but lost tau. So it's okay, it's kind of equal. Got it? In that way, I memorize. You may laugh, but that is the only way to remember. Anyway, so let's continue the topics related to the time averages. Now, this may be very difficult at the first glance. I still remember when I first saw this thing, when I was an undergraduate student, with our professor covering Peebles' book cover to cover in a semester, very, very fast. And I had no idea. So let's consider a random process, continuous time random process, capital X of t. Now, what we do is that we plug in this random process to the time average operator. So simply just consider some box, some system that computes the time average of the input. Before we used a deterministic signal as the input. Now we change it to a signal with uncertainty. It's possible, right? Now, what I'm asking is this. What is the output? Anybody? What is the output if we plug in a random process instead of a deterministic signal to the time average operator? So first, whenever you have this kind of question, so some random thing goes in and what is the output? Just consider something, sample something. In this case, you have sample path, for example, X of t. What is the output here when your sample path goes in? If it converges, it's a scalar, right? Right? If X is a real number, that is a real function. Output is a real number, or does not converge, right? If it converges. If it is a complex number, a complex valued function, output is a complex number. Now, suppose X of t is a real valued random process. Then output is scalar, real scalar with uncertainty, because you don't know what is the realization of X of t. So in this way, you understand that the output must be a random variable because it's scalar with uncertainty. So it's a random variable. Got it? So that must be the first thing you have in mind. Now let's take a look at the expression. So x of t is what? Random process. And it's integrated. What does that mean at all? What does that mean? You may say that just integrate sample paths and consider some randomness. But precisely speaking, in order to precisely speak, we'd better use our measure theoretic notation, even though we do not much cover about measure theory, but you know the measure theoretic notation or way to describe a random process. What was that? We always start with an abstract probability space that describes some random experiment. And here comes an outcome. And here is a box that maps this single something. We don't know what? Because this sample space and abstract space, it could be a set of numbers. It could be a set of some banana, strawberry, something. We don't know. But anyway, what is important is that that box maps this S to something. But in this case, time function, right? And we say the output, we denote output as x of t. If it is a continuous time, then we usually x parenthesis of t, right? So this is our idea. Now, what we do is that here we put a time average operator. Then what do we have? We have this one as the output. Got it? Now let's see what is this. This gives us some number, real number, as our argument. So we may call this as something, a function of S. That is this one, right? Real number. And we know immediately that, hey, that's a random variable. Because when we have something that generates some real function of S, we call it a random variable, real random. If it's a complex function of S, then it's a complex random variable. So let me repeat. Time average of a random process is a random variable. Got it? You have to understand this. My professor didn't spend this much time. Got it? I kind of mentioned this repeatedly, probably 20 times or 30 times for more time. Anyway, so first question, what is X bar? This is X bar. It's a random variable. Got it? You have to understand. However, as we've already seen, time average involves limit operation, which means that the quantity may not converge. So that's a big headache, actually. So we will talk about it later, but anyway. So whenever you have some fundamental question, then you'd better go back to measure theoretic notation of random variable, random vector, random process. That makes almost everything clear. So that's why I mentioned the measure theoretic approach, even though I do not talk much about measure theory. Anyway, now as we have done to a deterministic signal, let's take a more in-depth view of this one. So we have some limit operator. And what about this one? this one could be parameterized by some S and also the capital T, right? So if we change capital T, then we have a different, in general, random variable. Now, how many random variables do we have now? Uncountably infinite random variables. However, these uncountably infinite random variables are also ordered, right? If capital T is 1, that iterates for small interval. If capital T is 100, then it iterates for a long time, right? Now, we take T into infinity. Then what happens? We now have to consider the limit of parameterized random variables, a limit of infinite random variables. Now, let me ask you a question. Suppose you have in high school some f of x. Now you want to compute this one. What's the difference between getting this limit and that limit? Here, you specifically take natural number or some number that tends to infinity. And so kind of you have a continuous parameter signal and you have a sequence of real numbers, right? Are they the same? So my question is this one. Given a function f r into r, are they the same? Anybody? Of course, they are in general different, right? In general different. For example, this may not converge at all. For example, f of x is sine x. Sorry, sine 2 pi x. It does not converge. But if you sample that kind of at every integer, it's 0, right? So it converges. So be careful. They are not the same. However, if this exists, then they must be the same. Otherwise, we have a contradiction. So got it? So if this converges, then they must be the same. So we are going to rely this trick again and again. So assuming the limit exists, we just, for example, consider not the uncountably infinite random variables, but some sequence of random variables by specifically sampling, for example, at some integer or integer times some constant. Got it? Then what do we have here? This is very important. We have to talk first about the convergence of a sequence of random variables first. That is this one. That corresponds to this one. Okay? The problem is that in order to clearly understand the convergence or divergence of a sequence of random variables, you have to have some knowledge about the convergence or divergence of a sequence of real numbers or complex numbers. And unfortunately, in our high school, not in university or college, in high school, we didn't carefully define the limit of a sequence. We just say that, okay, if it's similar to engineering sense. Hey, for sufficiently large n, what is the value of the sequence? And does it seem converge to something? If that is true, write your answer, something like that, right? So for example, suppose you are given a sequence, x sub n equals 1 over n. Now, what is the limit of this sequence when n tends to infinity? You say 0. Right? But after you enter the college or university, what happened? In your first calculus course, I still remember that day when I was a freshman, professor just said that, okay, let's define the limit of a sequence of real numbers. I said that, I already know that. And he just started to, how to say it? The talk, he started some kind of, how do you say that? Yeah, it was like this. For every epsilon positive, there is n of epsilon, blah, 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 blah. And suddenly, epsilon started to be involved. And he talked about some n of epsilon and blah, blah, blah. And do you remember that? Everybody still familiar with that definition of the limit of a sequence of real numbers? So that is some big issue. Another one is that what is a random variable, by the way? We already once talked about that. It's a function. So if you have a sequence of random variables, actually, you have a sequence of functions. Now, do you have, or have you been exposed to the convergence issue to a sequence of real functions? Actually, yes, we've done at least once, because you all has taken the signals and systems, and there the professors talked about Fourier series, right? So suppose you have a square wave and with period some capital T, and your professor rewritten this function, this continuous function, as a sum of countably infinite number of sines and cosines. You remember? And probably he or she have said that okay, we may truncate the signal and observe. And what happens if we add enough number of terms? Then the approximate function is very close to the rectangular function, right? Rectangular square wave. But still, at the discontinuous point, we have some ripple. And interestingly, that height of the ripple does not reduce, even though we add more and more terms. What we get is that the energy, so the width of that overshoot and undershoot reduces, so that the energy of the difference signal, so you take the difference between the original square wave and your truncated Fourier series, you subtract and take the absolute value and square, and you integrate over one period. That error energy of the error signal converges to zero. Something like that. You remember that? And that phenomenon was called what? Gibbs phenomenon, right? So you are exposed to an issue of the convergence of a sequence of real functions or complex valued functions. Similar thing happens here in this course. So in order to deal with time average of a random process, if it converges, in order to talk about something, we have to at least have the convergence issue of a sequence of random variables in our mind. And that is closely related to the convergence issue of a sequence of real functions. Got it? So now you understand why we are going to talk about convergence of a sequence of functions, because convergence sequence of random variables is a special case of a sequence of functions. Got it? And there are many modes of convergence of a sequence of functions, especially when we say that the function is a random variable. Then there are 4 important types or modes of convergence. It's like this. Probably some of you have taken advanced calculus course where when people talk about convergence of a sequence of real numbers, first, the limit of a sequence was defined. And second, sorry, let me say it. definition. X of n converges to X if for every epsilon positive, there exists the integer of epsilon in n such that the difference between xn and x is, let me say, less than, I must be careful, less than epsilon for all n greater than or equal to n over epsilon. So this is the definition I still remember. Yeah, I believe so. Usually they put something like this. Yeah, I believe so. Anyway, that is the definition. But here in this definition, there is something interesting. We have to have so-called the limit in our mind before we check whether xn converges or not. Got it? So it's like this. You guess the limit. By the way, if this holds, this is called the limit of a sequence. The limit of this sequence. So somehow you already have a candidate limit. And then you check by using this definition. And if this holds, then the sequence converges to the limit x. But this is somewhat strange. We want to have some other method to check whether a sequence of real numbers or complex numbers converges or not. That is discovered by Cauchy. So there is another definition by Cauchy saying that if a sequence satisfies some condition, blah, 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 then Cauchy is going to call the sequence is a Cauchy sequence. So which means that here, this is the set of, for example, all sequences of real numbers. Got it? So let's focus on a sequence of real numbers first. Got it? Then there is a very small set, very small subset where, so here, if I say that, here is a very small subset, and here is an element or member of the set, which means that that X corresponds to a sequence of real numbers, right? For example, X of n equals 1 over n, right? So this point corresponds to a sequence of real numbers, a specific sequence. And this is called the set of or convergent sequences of real numbers. So if the limit exists, you can classify this as a convergent sequence. The problem is that if you want to use the definition, you must have your target limit in your mind. But Cauchy have found something very interesting. He defined some other set. So this is the set of Cauchy sequences. So if some property is met by a sequence of real numbers, that sequence is called a Cauchy sequence. Got it? So it's a subset. In general, they may have some intersection or not, right? One of this may contain the other, right? What happens? Interesting thing is this. Every real Cauchy sequence converges. Every real Cauchy sequence. So in this case, if Cauchy, it converges. What does that mean? This sequence is a subset of that one. And if I remember correctly, the way around also holds. So in real case, the Cauchy sequence converges and vice versa. So if I remember correctly, I'm not sure, I almost forgot, but in real sequences, they are the same. And also, if I remember correctly, in complex, so you have a bigger set, the set of all sequences of complex numbers. Even in that set, if you find the set of all convergence sequences, complex value sequences, and you have Cauchy sequences, they are the same. Be careful. In general, abstract set of sequences of some abstract entity, it does not hold. Got it? And we are going to see that. Anyway, so some of you already been exposed to the notion of the convergence sequence and a Cauchy sequence. But there is more than that, especially when we talk about the set of sequences of real functions. And we are going to talk too much about that today. We are going to quickly see one of the definition. So here, let me repeat. If you are given a sequence of real numbers or complex numbers, there are two definitions. So convergence sequence or Cauchy sequence related to the convergence, they are the same. Got it? However, if you have a sequence of functions, then there are different definitions of convergent sequence of functions. So when you say a sequence of functions converges, you may have slightly or drastically different definitions. The first thing is simply a pointwise convergence. Second one would be a convergent in piece mean. Third one will be convergence in measure, blah, blah, blah. Also, there is a very strong definition of convergent, uniform convergence. By the way, if you have taken introductory real analysis written by Rudin, probably you've already seen that the first half of the book emphasizes the uniform convergence. Because if a sequence of functions, real functions, uniformly converges to a function, then you have a very nice property. For example, suppose you want to know the integral of the limit function on an interval. Then you can compute the sequence of integrated that function and take the limit. So integration, as I told you, is already a limit operation, as you know. And that limit n tends to infinity is also a limit operator. You can change the order of these two limits. And some of you may say that, hey, that's I've always done. You are right. In most of the engineering problems, we just, without feeling any guilty, we just interchange the order of something. Like, hey, let me exchange the order. Is there anything wrong? Somebody say. Does this hold? In general, no. Okay. Here goes the counter example. Suppose this f of mn is this function, m over m plus n. Then what is the first limit? So you take, be careful, here you have to put the parenthesis here, right? If you have a double limit. So what is this inner limit? N tends to infinity. This is 0 for any m, right? So limit of 0. So left side equals 0. What about the right side? This inner limit is 1, whatever n you have. Then the limit of 1 is 1. So they are different. Got it? So in general, you cannot interchange the order of two limits. And suppose you have a sequence of functions. And suppose this function converges somehow, in some sense, to f of x. Now you want to compute this integral. And the question is it the same as? And now your answer is that, in general, They are different because integration is a limit operator, similar to that one. And here, what you have done is this one. So here, you change without feeling guilty, the order of two limits. And you may say that, hey, this is f of x. Got it. This is very dangerous. Okay? So in general, you cannot change the order. I asked you whether they are the same. And the question is equivalent to ask that can you change this limit and that limit? Because this is similar. This is simply the same as this one. Got it? So in general, this does not hold, but if this convergence is a uniform convergence, then you can say that. So uniform convergence is very important. And it makes almost everything possible. Even you can change the order between limit and differentiation under certain conditions. However, the set of uniformly convergent sequence of functions is very small. Of course, it's very strong and they have very good properties. So the set is very small. So it's not used to define the convergence because in some other applications, this is strong, very restrictive definition of convergence of a sequence of functions is not necessary. Similarly, when we talk about the convergence of a sequence of random variables, uniform convergence is never useful. So we are happy. So we just never talk about uniformly convergent sequence of random variables. However, this random variable is related to so-called the probability measure. We have something different from ordinary convergence issue of a sequence of real functions. That's why we have different modes of convergence. One of them is very easy to understand, so I'm going to introduce you today. But for other three convergent type or convergence type of modes, we will defer our discussion. Here, the mean square convergence. So sometimes converges in the mean square sense, we say, is simply this. So you are given a sequence of random variables. So here you have x sub 1, x sub 2, x sub 10, x sub million. So you have countably infinite number of random variables. Now, it converges to a random variable, x, in the mean square sense. This is the definition. So we say this if, right? If what? We just kind of move this to the left side. Then we have x sub n minus x, right? That converges to what? 0 in the mean square sense. See that? Mean square of the difference, right? So it's like our logic is this. From here, we somehow convert this to that one. So, okay, xn minus x converges to 0. Be careful. Here, 0 is what? 0 function, actually. Because this is a function. Random variable is a function of s, right? This is a function of s. So this is a function of s, but always the value is 0. Now, mean square sense. Okay, so this convergence is mean square sense. So we put this guy here and say that, okay, converges to mean square. And we know what is this, right? This is 0. So expected value of the difference between the nth random variable and our limit random variable. If this converges to 0, be careful. What is this? This is a number, right? If we compute the expectation of some random entity, especially random variable, right? We have a real number. So now we have a sequence of real numbers. So you may say that this is some say A sub n. That sequence converges to now a real number 0. Got it? This is the mean square convergence of a sequence of real random variables. Okay, also this can be extended to complex random variables. And this is very easy to understand and in many cases easy to compute and also very, very useful. And in many cases, it also has engineeringly non-problematic convergence. It also implies some other convergence mode. I said there are four different definitions of convergence of real random variables. Fortunately, it's like this. The four are not totally unrelated. They are related. Here, almost sure convergence you have. And here you have convergence in the pth mean. Here, p can be any real number greater than or equal to 1. So it includes the p equals 2 case. That is the mean square convergence. So here you have uncountably infinite convergence, actually. But we can just say that in the pth mean. Now, this implies convergence in probability. Also, these all p greater than 1. So you have uncountably infinite, actually, modes of convergence. They also imply convergence in probability, and they all imply convergence in distribution. So even though we are going to study 4 different types or modes of convergence of a sequence of random variables, they are related in this way. Sometimes we really need that one in our engineering problem. But sometimes proving the convergence in the mean square sense is very easy. Then we do not directly prove that one, but this one with p equals 2, because it's easy to compute. It involves only the second order moments, right? So we easily compute and say that, hey, I've shown that the sequence of random variables converges to a random variable in the mean square sense. So it also converges in distribution. So probability converges to probability is some number, and we are happy, something like that. Sometimes we need this one in probability convergence. And we also use that one, for example, mean square sense. So mean square convergence is very, very useful. You'd better remember that one for now. Got it? Now, let me go back to this one first. So here you have, sorry, let's use our simple notation. So you have a random process and calculate the time average. Let me ask you again, what is it? And then you have 2 steps. Okay, let me plug in a sample path. I have a real number, but now I have uncertainty. So real number has uncertainty. The output is now a real random variable, right? That is the one. But when you write down in your exam or in your thesis or something, you better use this one to look professional, right? And to be clear. So you have a function of s parameterized by t. So you plug in here, and if this converges to something, that must be what? A function of s, right? So here, that function name is used x bar for convenience, and s. So you have a measurable function of s, which is by definition a random variable. Got it? Now let's do something similar. What is this one? Are you familiar with that? So here you have a random process, capital X of t. Now you advance it and multiply by itself after conjugation. Hey, something familiar, right? So this guy has conjugation and that guy has tau. Okay. And now you plug in. What was that? If x was a deterministic function, we called it a time autocorrelation function. Auto means self, right? Correlation means that if tau is 0, then that correlation value would be the highest. But anyway, now let me ask you a question. What is this one if it converges? What is this? Of course, you can just use your definition here. Limit t goes to infinity, 1 over some period, same as this integration interval length. And you write here. What is this one? After you integrate it, you have, in general, something parameterized by tau, right? And also, it has some uncertainty. So in a major theoretic sense, this must better written as something like this. So x t plus tau, x t conjugate, sorry, of s. Am I right? So using major theoretic notation, this integral divided by 2t had better be written in this way. Now you integrate with respect to t, and everybody will agree that this is parameterized by capital T and tau and s, right? But usually we drop just the dependence on s and saying that that is random something, right? But we take the limit. So this is what? Now parameterized by tau and s. So we, in general, we say that something of tau by dropping s. That's why we have that one. And actually, this is similar to the previous notation. What was that? When we had the deterministic function, we had this notation. Here, lowercase x, and here, just capitalized x. The same notation they have, right? So now you have what? A random variable parameterized by tau. Got it? So it's a random variable parameterized. So this is what I've just talked to you, right? So here, as I told you, when you take the limit, we have a sequence of random variables. Even if we choose this capital T after discretization. Right? So we have to have some knowledge about the sequence of random variables whenever we talk about time autocorrelation function over random process. Right? By the way, what would be the expectation of the time autocorrelation function of x of t? Expectation. See that after expectation, dependence on s disappears, right? But still, the dependence on tau remains. So in general, this would be a function of tau. Got it? Now, I have some questions. Suppose x of t, the random process, is stationary. What was the important motivation of the definition of stationarity? Translation invariance. So wherever you choose as time origin 0, the statistical property, the sample path would be different, right? Because we shifted the time origin, but statistical property of a random process does not change at whatever order. The nth order joint PMF or millionth order PMF does not change if you change the time origin. That is the definition of stationarity. And let's assume x of t is stationary, and that stationary process, our specific process, allows us to bring the expectation into integration. Actually, you know that expectation of a random variable is integration of some quantity times the density function, right? dx or something. So expectation involves integration, and integration is a special case of limit operation. So here, expectation can be brought inside the integral, means that you can change the order of to limit operation. And you know it's very dangerous. But let's assume that for now, okay? Then let's see what happens. And also, in many engineering problems, not all, okay? Especially in some network theory, that is very important. But in many physical layer problems, that changing the order doesn't matter. That's why the physical layer professors and engineers are not that precise in the real analysis and measure theory. But network professors and engineers, they are very picky. They are almost mathematicians. Anyway, so let me ask you, what is this one and what is that one? What can we say about expectation of X bar? By the way, what was X bar? Time average of random process. So what is the expectation of time average of the random process? And what is the expectation of time autocorrelation over random process? What can you say? So let's just use this hint. So let me first rewrite that one. What is that? That is time average of what? Random process. What is this? Time average of x of t plus tau, x conjugate of t. If you dislike to use brackets and brackets, you can change the brackets, curly brackets, parentheses, but it doesn't matter. Now, so this is a limit operation. This is a limit operation, right? You change the order, means that if it is allowed, then it's the same as time average of expectation of x of t. By the way, what can you say about expectation of x of t for stationary random process? It's a constant function of time, right? Because it's first order moment, and that should not depend on t, right? So it's a constant. Let me say C, and that is time average. So it's same as C. So you can say that this equals expectation of x of t. Strange notation. Be careful. See that? This is expectation of a random variable, right? This in general is what? Expectation of random process, which is a function of time. However, that is constant for all t. So this is not a function of t. That's why we can say that they are equal. Be careful. In general, they can never be equal because right-hand side is a number and left-hand side is a function. They cannot be equal, right? However, if a function, the function is a constant function, we can say it. So strange thing happens. If we allow, we assume that the process is stationary and we can change the order of limit and time average, expectation and time average. And this actually gives us a very good idea about the estimation and detection theory. Last time, I suddenly talked about the 645, the statistical signal processing course, where you will be taught about the detection theory and estimation theory. They are all a kind of statistical inference, right? And while talking about that, I said that, hey, but when you observe a random process, especially, for example, a continuous time random process defined on the interval from negative infinity to positive infinity, strictly speaking, even though you define the random process that way and you may have many sample paths, you can observe a single sample path in your life, right? So is it meaningful to talk about any statistical average, expectation or probability? You remember that? Even the probability can be rewritten as an expectation of some indicator function of subscript something, right? So whenever we talk about expectation, we have to somehow think about ensemble average But in our real world, if we just take the definition of random process literally, then suddenly that definition is useless, right? And we cannot make any statistical inference. You've seen some example. X of t equals capital R cosine 2 pi sum f0 t plus capital theta. And R and theta are random variables, for example, independent, Rayleigh uniform. Now, you observe that single realization of random process for 10 days. Can you talk about 2 days after? If you observe a single process, you can deterministically know whatever distribution R and theta have, right? But if you are asked, given that observation, you want to know some ensemble property of the process at 2 days after, you cannot say anything, right? If you are not provided by the distribution of R and theta, you cannot guess anything because you observe only single path. But sometimes observing a single realization of a random process may provide us some statistical property related to the ensemble average, probability of something, expectation of something. Not always, but sometimes. That kind of property of random process is called vaguely ergodicity. And ergodicity is usually related with time average replacing statistical average. So it's like guessing what is the statistical property of unknown parameters now can be exchanged to the time average of some past observation. So from past observation, you learn statistical property, probabilistic distribution of what you are modeling, and you use that for predicting or detecting something. Does that sound very familiar to you? Yeah, that's what is done in AI model. So you have some observation, data, training data. Using that, your model is trained to extract some ensemble property. Now, you are given new input, and what you do is some inference. That is actually, in most of the cases, can be converted to a form of statistical inference. So our communication and signal processing engineers actually have been doing something related to artificial intelligence and machine learning. But our emphasis was not heavy on the training, especially using computers, because in our case, building a system that responds very quickly was important. So we wanted to reduce the computational cost and computational time. But in many applications, we may have very good facility, supercomputer level facility that can use tons of data, past data, to extract the statistical property of data. That is called training now, right? And after the training, amazingly, only some, that's million in many cases, but some coefficients are taken, and even it can be copied to many new inference machines. And they can work in India, in South Korea, in the US, in Canada, and they admit some new random observation and generates the point estimate or guess of the maximum a posteriori probability guess, something like that, right? So it's time's almost up, but what I want to say is this. So from today, we are going to see something like this. You want to compute the expectation of something that is definitely related to ensemble average. Somehow, under certain conditions, not always, under certain conditions, that can be computed by, this is typo, right? Yeah, something's wrong. Yeah, definitely wrong. Okay, got it. So I'd better say, yeah, later. Anyway, we will see something like this. Time average replacing statistical average. Got it? This is not a good, very good example, but in this case, just time average disappears in this example. However, in many cases, time average replaces some ensemble average. So single realization of random process may provide us tremendous information under certain assumption or under certain condition. That is the key we are going to use later. So let me stop here. We have some technical difficulty in the beginning of today's class meeting. So today's meeting was relatively short, but just before the exam, you are happy with that, right? So yeah, up to this point, let me just extend. Up to that point is the coverage of the midterm. Got it? So let me stop here.